Hello everyone, welcome to the 13th tutorial class on digital communication. In earlier class, we have discussed about the two others digital modulation technique. Those are ASK amplitude shifting and FSK frequency shifting. In this class, we will discuss about the other type of digital modulation technique, that is binary phase shifting or BPSK. It is very efficient digital modulation technique. The reason behind this comment will be elaborated later. Now, what will be covered in this lecture? That is the initially we'll observe the different property of the BPSK and like spectrum, bandwidth, and the signal space diagram, error probability, etc. And after that, we'll discuss different generation and detection technique for the BPSK. Now coming to the first slide about the PSK or BPSK. Basically, PSK and BPSK both are synonymously can be used. Now the property of the BPSK is like that phase of the sinusoidal carrier will be shifted. Frequency shifting, from the name suggests, from the name we can easily say that the phase of the sinusoidal carrier will be shifted depending on the input binary bit. Now, if the input binary bit is 1, the initial phase angle for the carrier will be 0 degree. Whereas, if the incoming bit is 0, the initial phase angle for the carrier will be 180 degree. However, for the BPSK, frequency and the amplitude of the carrier will remain unchanged. But what property will be changed? The phase of the carrier. That's why we call it as the BPSK or binary phase shift key. So we can see that this one is the an arbitrary bit sequence like 10111010 like this, and this one is the carrier wave. So after the BPSK signal generation, we can see that uh, whenever there is 0, the corresponding phase of the carrier signal will be changed like this. So for the uh, initial bit 1, the corresponding carrier, the phase of the corresponding carrier is 0 degree, so it is similar to the carrier signal. But whenever there is 0, the corresponding phase of the carrier will be changed by 180 degree. That's why it will start from here. And again, when 1 will be started, then the corresponding frequency will phase angle will be 0 degree. So it will be, and as the two there are two consecutive bit as 1, so there will be no phase shift in between them. So like this, uh, BPSK property will be maintained. That means if there is 1, no phase shift. If there is 0, 180 phase shift. That is the property or rule of the BPSK. Now coming to the mathematical expression of BPSK. So for 1, we can write, as there is no phase change or phase shift, so you can write that for 1, the corresponding modulated signal can be given by a cos 2 pi fct, and a will be substituted by root 2 ps cos 2 pi fct, and it can be expressed in term of energy signal like this, plus 1 multiplied by root over eb into 2 by tb cos 2 pi fct. However, for 0, the modulated wave have the phase shift of 180 degree. So you can write the corresponding equation as like this a cos 2 pi fc plus 180 degree into t. So you can write like it can be written like this. So minus root 2 ps cos 2 pi fct, as we already know, cos 2 pi fc plus 180 equal to minus cos 2 pi fct. So after that, it can be expressed in term of energy signal. So it is minus 1 multiplied by root over eb into 2 by tb cos 2 pi fct. So overall, we can write that st bpsk is bt into root ev into root 2 by tb cos 2 pi fct, whereas bt is plus 1 when 1 is transmitted, and it has value of -1 when 0 is transmitted. Okay, so if we closely observe the input binary sequence like 101101, so it is basically unipolar energy. So 1 is represented by 1 volt and 0 is represented by 0 volt. However, when we consider BT, we can observe that when 1 is transmitted, then corresponding value of BT is +1, and when 0 is transmitted, corresponding value is -1. So basically, if you observe the corresponding waveform, it is similar to the energetic polar types of signal. Okay, so you can see that this is polar. The property of the polar signal is that for 1, we get the plus a volt, plus a by 2 volt, and for 0, minus a by 2 volt. So you can see that for 1 we get 1, and for 0 we get -1. Hmm. So we can see, we have observed uh, the corresponding mathematical expression like this: ST BPSK is BT into root over EB into root over 2 by TB cos 2 pi FCT. Now coming to the signal space diagram of BPSK. So from the earlier equation, we can write that BPSK is like this: BT into root EB into phi 1t, whereas phi 1t is root 2 by TB cos 2 pi FCT, and BT can taken as value as ±1. So if 1 is transmitted, it can take +1, and if 0 is transmitted, it can take -1. So by considering this fact, we can draw the signal space diagram. So whenever we want to draw the signal space diagram, basically what we want to do, we want to find out the corresponding energy level at the with respect to some kind of real valued function. So if we observe BPSK signal, so here you can see that real valued function is cos 2 pi FCT, and and the equation is equation contain an energy signal part, or in term of it is expressed in term of energy. So basically EB is nothing but energy for a particular bit, root EB. So our initial objective to draw signal space diagram is to identify phi 1t, or other, it may be phi 2t. That means we need to identify some orthonormal real valued function. Like for FSK, we have already observed there are two real valued function: cos 2 pi FCT and cos 2 pi FC, sorry, cos 2 pi FCHT and cos 2 pi FCLT. So that's why we use two real valued function, phi 1t and phi 2t. But here in case of BPSK, corresponding binary expression, geometric representation will be given by this: BT into root over EB phi 1t. So and root EB, this is basically the energy, phi 1t is the real valued function, and BT can take ±1. So if you want to find out the corresponding energy level with respect to phi 1, we will draw an axis. So if here for BPSK only one type of real valued function has been observed, so we have drawn only one axis. Now it can be observed that BT can take either +1 and -1. So for 1, the corresponding energy level is plus EB, and for 0, corresponding energy level is minus EB. So now if you locate, or if you point out that location along the axis of phi 1t, so we can say that for 1, the corresponding energy point will be root EV, and for 0, corresponding energy level will be root over minus EV. Okay, so this one for the symbol 1, and this one for the symbol 0, and the distance between them obviously will be root EV plus root EV, that is 2 into root EV. So this is basically the signal space diagram of BPSK, where an axis has been drawn with respect to phi 1t. Next we want to point out the location where the energy level for the symbol 1 or 0 is located. Now next our objective will be to find out the distance between them. The more the distance will be, the corresponding digital modulation technique will be more noise immune, or it has less error probability. So here you can see that the distance between two symbol for BPSK is 2 into root over EB. Whereas if you can remember that the distance between two symbols for ASK is root EB, and distance between two symbols for BFSK is root 2 EB. Okay. Whereas in case of BPSK, it is 2 into root EB. So the distance between two symbols for BPSK is maximum. So from here we can conclude that the error probability is least for all other digital modulation technique. That means it is most noise immune digital modulation technique. That's why we have already told that it is very efficient or most efficient digital modulation technique over others. I think signal space diagram for any digital modulation technique is clear to you. That means how can we draw a signal space diagram for a particular modulated waveform, digital modulated waveform. So that is the process. Now coming to the PhD of BPSK. So here, as the mathematical equation, if you observe the mathematical equation, there is BT into root EB into root 2 by TB into cos 2 pi FC term. So for the presence of cos 2 pi FC term, the total frequency, the total spectrum of the original baseband signal or original initial binary bit will be shifted to the plus minus FC. So we can say that the PhD of BPSK consists of two parts, where the baseband spectrum has been shifted to plus FC and minus FC. And from above figure, it is very clear that the bandwidth of the BPSK is, you can see that the maximum power is lying in between this FC plus FB and FC minus FB. So the practical bandwidth, we can say that BPSK of is FC plus FB minus FC minus FB, that is 2 FB. Okay, so that this is the basically the practical bandwidth of BPSK. However, theoretical bandwidth is obviously infinite, but we will consider the practical bandwidth here. So we can conclude that the BPSK is more efficient as it less error probability and less bandwidth. For FSK, the bandwidth is larger, like which is 4 FB. Now coming to the next slide, that is the generation of BPSK. Uh, Again, the equation for BPSK is given by BT into root EB into root 2 by TB into cos 2 pi FCT, and we already observed that BT is similar to the enhanced polar signal. Okay, so whenever we want to uh, generate BPSK signal, so initially what we have to do, we need to convert the initial bit, which is input unipolar energy type of data, into the polar signal. So we need a converter that convert the unipolar energy into the polar energy. That means we will convert the initial bit into the BT. Okay, now if we multiply that BT, that means output of this, you can see that that is unipolar to polar converter. Now it convert the unipolar input data into the polar data. Now if we multiply this polar data into the with the carrier, that is root 2 ps into cos 2 pi FCT, by using a product modulator or multiplier, so what we will get? We get the corresponding mathematical equation, and we get the, which is nothing but the BPSK. Okay, so this is the simple approach. It has been uh, so for BPSK, what you need to do? We need a converter and product modulator. The converter that convert the unipolar to the polar, and after that, course, if we multiply the corresponding output with the carrier, we get the BPSK. Now coming to the detection of the BPSK. So uh, for the detection, that means our objective is to extract the original bit or extract the baseband signal from the modulated waveform of BPSK. So obviously there are two types, non-coherent detection and coherent detection. Let's discuss about the non-coherent detection. So the non-coherent detection for the BPSK consists of this part. First one is the square law device, next one is the BPF, next is the frequency divider, next one is the multiplier, and you can see that the uh, input of the multiplier are the initial BPSK and the output of the frequency divider, and the next output of the multiplier will goes to the both integrator and bit synchronizer, and ultimately the output of the integrator is nothing but the corresponding demodulated bit or signal. So let's see how non-coherent detection has been operated. So this is the basically initial BPSK signal. So we can know, we have already know that it can be expressed like this: BT into root 2 PS cos 2 pi FCT. Now first one, this signal is passing through a square law device. So whenever it is passing through a square law device, what will happen? That means total signal will be squared. Okay, that means it will be like b square t 2 ps into cos square 2 pi fc. Now bt can take two value, either plus 1 or minus 1. Now if we make a square of that, that means all the value will become plus 1. So ultimately what we will get, the output is 2 ps into cos square 2 pi fc. Now if you neglect that term, initial or amplitude term of this signal, that is 2 ps, so we can write the output of the square law device as the square sorry cos square 2 pi fc. So we can write that output of the square law device is cos square 2 pi fc. Now it has two term, one and it can be expressed like 1 plus cos 4 pi fct. Now if this signal is passing through a band pass filter which has center frequency of fc, sorry 2 fc, so obviously it will pass cos 2 pi fc term, so we ultimately we get the cos 4 pi fc term. Okay, so next we have seen that this signal is passing through a frequency divider. So as the name suggests, it divide the incoming frequency into half. So the incoming frequency is cos 4 pi fc and the corresponding output of the frequency divider is cos 2 pi fc. So what we have now? Al After these three step, square law device, band pass filter and frequency divider, we have the carrier signal, okay, which is not known to us. Now if we multiply this cos 2 pi of fct into with the original BPSK, that is bt root 2 ps cos 2 pi fc, what we get? We get bt into root 2 ps cos square 2 pi fct. Okay, so ultimately the main objective is to identify the carrier signal. So for this purpose we have used these three block blocks: square law device, bandpass filter and frequency divider. Okay, now so you can see that, so the output of the multiplier will be bt into root 2 ps cos square 2 pi fc. So bt into root 2 ps, now we can express like this: 1 plus 4 cos 4 pi fct. Okay, now if it pass through a and sorry, if it pass through an integrator and bit synchronizer. Now there are two term, bit synchronizer. So bit synchronizer basically take care of starting and ending point of a binary bit. That means suppose the initial starting point is 0 second and the ending point is tv second. So bit synchronize, yeah, yeah, bit synchronizer will take care of that. That means 0 second, tv second, 2 tv second. Okay, next one is the integrator. Now what will do, integrator will do the integrate of the signal over a particular time period of tb. Okay, so if we take if we integrate the output of the multiplier, so we can we get this. So bt into root 2 ps integrate or integration of 1 dt plus cos 4 pi fct dt. As we already know, the average value of the integration of average value of a sinusoidal waveform over a full cycle, that means this term integration of cos 4 pi fct into dt is 0. Okay, so you can write the corresponding output is like this: bt into root 2 ps into tb. As we make integration over the only one time period of TB, so corresponding output is TB. Okay, so this is basically the output of the integrator, which is a DC voltage level. Now it has two polarity, so BT can take either plus 1 or minus 1. So depending on plus 1 and minus 1, the total value will be either positive or negative. Now if the corresponding output has positive polarity, then we can easily conclude that 1 has been detected, and it have it if the polarity become negative, we can conclude that the 0 has been detected. So this one is the basic operation of non-coherent detection, where we don't use any kind of locally generated carrier, but what we have done, we just initially extract the carrier signal by using square law device, band pass filter, and frequency divider. Now after that we just multiply that extracted carrier signal with the original BPSK, and it after it passing through an integrator we will get the ultimate output. Okay, so this one is the operation of non-coherent detection for BPSK. Now coming to the last slide, that is the coherent detection. So for coherent detection, at the receiver end, the corresponding carrier frequency has been known to us. So just we need to use a local oscillator to generate the original carrier frequency. So the process is similar to the non-coherent detection technique, except that the band pass filter, sorry, except that the square law device, band pass filter, and the frequency divider portion are absent. Okay, so all these parts are used for the generation or extraction of the carrier signal. But in case of coherent detection, as the frequency of the carrier signal is known to us, that means we know that what is cos 2 pi fct, so we just generate cos 2 pi fct using local oscillator, and it is go and the input of the multiplier is BPSK and the cos 2 pi fc, and the corresponding output is BT root 2 p is cos square 2 pi fc, and if it pass through integrator and bit synchronizer, we get the original signal or the corresponding bit. So the coming to the conclusion part, so in this class we have studied about the waveform, spectrum, and signal space diagram of the BPSK, and from the signal space diagram and the spectrum of the BPSK, we can conclude that the BPSK is the most efficient digital modulation technique over ASK and FSK, as the uh, bandwidth and the error probability is least for the BPSK technique. And after that we have also studied the generation and detection of BPSK. Okay, so these are the reference. Thank you.